Thank you. All right. Hello again to all participants. Uh, Welcome back to the regional capacity building on small area estimation. We are so glad to have you back here. I hope you still have spirit to learn more about a small area estimation. Last week, we have learned about our programming language. We also did a lot exercises on data modification, which is guided by our colleague from BPS-Statistics Indonesia. For today, I would like to welcome Professor Natapong. Yeah, as our resource person today, he's from Faculty of Economic, Thammasat University, Thailand. So as stated in on the agenda, today we will learn about regression model. We will learn about ordinary least square, generalized linear model, and also generalized linear mixed model. We will be guided by Professor Natapong. So without further ado, I will pass to Professor Natapong. Okay. Before we start, I would like to inform also that we can have a 5 minute break in the middle when we need it, and we will stand by guided by Professor Natapong. So now, without any further ado, I will pass the floor to Professor Natapong to start the session for today. So screen is yours, sir.
Thank you very much, and good morning, everyone. First of all, I'm not statistician. My background is economist, so please feel free to interrupt or to maybe add more information or more intuitions on the topics that I will present or I would like to share with you. Because honestly, most of my work apply small area estimate to explore the poverty or the income of people in the rural area, mostly in Asian countries. So today I would like to share the background or the fundamental of the techniques. And I know some of you earned the degree in statistics, and I'm sure that you have a better knowledge. And anyways, today I would like to share this one, the introduction to the simple regression on R. And for this week, we have 2 days, and on each day, I would like to do the sequential introductions. For today, I would like to introduce first the simple linear regressions, and then after the break, we will move to the next one, which is the introductions of the GLM, the generalized linear model, which is the modifications of the simple linear regressions. And honestly, all of my materials are based on the existing lecture notes or the code. So first of all, I would like to acknowledge the original code, and I already include the original source here. So you can also look at the source of each page that I already included the link to obtain the original materials. But first of all, I would like to acknowledge the contribution of the expert who produced the original material for us. And for this one, for the first lectures, I would like to use this material. It was published in the journal, and it's the open access one, so you can use this link to access the original papers. It was published last year. And basically, this one show the techniques to use R to do the linear regressions. And I think most of you already learned about linear regression, or some of you might have know the techniques. So sorry that my office is not soundproof, so sometimes you might hear some interruptions. And first of all, we would like to estimate these equations. I think it's the fundamental of the study, especially in statistical and scientific study, that we try to explore the relationship between y, which is the independent variable, and we would like to use x, which is the independent variable, to predict y. And basically, we have the straight line, we have the linear equation that show the relationship. So when we have a higher value of x, this equation show that y will increase if the slope or the beta one is positive. And I think basically we have the relationship like this one, that we have y and x, right? X is on the horizontal axis and y is on the vertical one. So we try to predict the relationship between x and y, and beta 0 is the intercept term, and beta 1 is the slope. So we try to come up with the best estimate of the slope and also the intercept that fit the data or can come up with the best approximation of the predictions. So this is the basic equation and the basic relationship that we would like to explore the techniques and would like to use the statistical software packages to estimate these equations. I know some of you might have experienced the technique on other software packages like Stata or SAS or SPSS, and R is the open source one. So I know that it might be the inconvenient at the beginnings to switch to use R to learn R, which is the new environment. But the advantage of using R is the open source environment, because it's the open or the public community that share and produce the software and the latest versions of the technique. So we don't have to worry about the license or the copyrights or the legal issues. We can use and install R on all platforms, and also is keep updating. And so today I would like to share with you the code or the step of using R to run the linear regressions. And back to the fundamentals, we try to come up with the best slope or the best beta. And it is very crucial, because if you have the accurate beta, or you have the most efficient one, it will ensure the relationship, right? Because basically we want to understand the relationship between x and y, and if beta 1 is positive and statistically significant, it's confirmed that when x increase, y will increase. And also we can have the negative beta 1, it can be the negative relationship. So when the x increase, y will decrease. Sorry for my sketch and my handwriting. So we can also have the case that the beta 1 or the slope is negative and statistically significant. And also the estimation give the value of intercept term of beta 0. And intuitively, beta 0 is the best guess of the y if x is 0. Right? I think some of the student or some of the people who first learn the linear regressions, and they ignore the significance of the intercept term or the value of B0. Or I think in some textbook they use alpha, but we still need the intercept terms, because it show the existing value of y without x, right? Even though we have x which is 0, we can come up with the best case of y, which is the intercept term. So y still exists without x. And also the value of beta is this, beta 1 is slope. And typically we come up with the quick estimate of beta from these equations. So if you look at these equations, we can quickly compute the value of the slope because we only need the value of x and y, and then we can compute the slope here. So we don't need other calculations. We just use this simple matrix calculation or the matrix algebra here to come up with the value of beta. So I think this is very important to understand the intuition here that actually the slope is based on simple calculations, the high school mathematics that you just need the fundamental of metric algebra to do this one, the x transpose times x, right? Or the multiplication of x transpose and x, and you inverse this result, and then you have the other term, which is x transpose and y, and you have these multiplications, and then at the end you get the last result, which is the multiplication of these two terms, and you come up with beta. So please keep in mind that the slope is come from this simple calculation. You don't need any statistical tests for the slope. Okay, but anyway, we still need the statistical distribution to ensure that the slope is not zero. So I think in the textbook or in the theory, they will call the best one or the best slope as the blue estimators, or the best linear unbiased estimators. And let me share with you. I think some of you might have learned or already know about this fundamental, that the blue is the properties or the characteristic of the slope. And yes, we want to have the best one, and now we're working on the linear relationship. That's why we call this one the best linear estimator. But also we need the unbiased estimators. Okay, so the unbiased means the means of the beta is very close to the actual values or the actual means or the actual average. And we need to satisfy this property. So in the textbook, in the theoretical foundations, there are the proof to show the conditions to ensure that you will get the blue one or the best linear unbiased estimators, and it will examine the relationship inside the variance covariance matrix. And the variant is the error terms, right? Because from the step-by-step calculation, first you can quickly come up with the slope from this calculation. You need only x and y, which is actually the input, right? The input our calculation, we need dependent variable and independent ones. And if you know both, you can quickly come up with the slope from this calculation. And with the slope, you can also compute the value of the projected or the estimated straight line here, and then you have the actual data. So you can also obtain the residual term or the error term. And the error term becomes the crucial part of the linear regression, because the error term or the residual will be arranged, or will be the main part that construct the variance covariance matrix, right? You need this term. And then you have the matrix, the square matrix, that is the result of the multiplications of the variance covariance, the error term or the residual. And then you get the variance and covariance value of this residue. And the property of this matrix will determine the quality of the regressions. And if you satisfy all conditions, you will get the best slope or the best estimator of the beta here. And since we have limited time, and this is not the technical sessions, I would like to skip all of the proof. But if you have the fundamental in mathematics, especially in linear algebra, so not linear algebra, but in the matrix algebra, I think this is a fun proof, and it's really intuitive to learn and understand why the quality of regression depends on the variance covariance matrix, which is the multiplications of the residuals. And again, we will check the quality of the variance covariance matrix here of the error terms in our code or in our example today. And I will switch between this lecture note and also the screen of my R Studio. And I use the code that included in these publications or in this paper. That is my main reference one. And I modify some of the code, but I think the majority of the code are still intact or still included in this example. And I think you already learned in the previous lecture that in R, you may first start with this slide, which is the cleaning process, that you have to clean all existing values in the system. So you may use this slide to clean existing code and also existing variable, existing value that are kept in the memory of the computers. And in R, you have to set the seed to preserve the value of all inputs and all results. And this will keep the results or the process to be reproducible. You will get the exactly same values, the same results if you set the seed. And then in R, we have to install the package, actually packages, because in the standard version of R, the software just includes fundamental calculation or fundamental capability to do basic calculations. But if you want to extend the capability of R to do the computation specifically for your studies or for your maybe specific calculations, you have to install the package that also provide the code or provide the tool on the existing command for that calculations. So in this example, we need these packages to do the calculations. So first thing first, you have to install the package here. And this is the example that you may use this set of the code to do the sequential installations. When you run all of this code, R will pick up each name of the package and will install the package. It will automatically download the package from the website, from CRAN website, which is the central deposit of the package, and it will automatically download that code or that package to your computer and install each one into your R system. And also we need or you can do this one manually. Okay, there is the menu or the top menu of the R environment that you can just type the names or search for the specific package and install each package into your computers. And I think the latest version of RStudio will do this one automatically. It's very smart. I think it's already embed some kind of AI into the the environment of the RStudio. So it will scan your code, and if it detects the package, like the name of the package, and it will also check the existing package in your system, and if it's not available, it does not exist, the RStudio will automatically download and install the package for you. So I think if you use the latest version of the RStudio, you may not need this part of the code, because R will automatically scan and try to uninstall the packages for you. But anyway, if you use the old versions, this is the first step to do the calculation. You have to check the availability of the R packages on your system and try to install the new one, or the one that is required in the code. And after you already install the package, in this example, the data is already included in the package. So you don't need to import the data. You just call the data here. The data set is rail trail, which is the data set that include the temperature and environmental factors, like the high and the low temperature, the average temperature, and the seasons, like spring season, summer season, falls, cloud cover, precipitations, and then the last one is the main variable, is the volume of the transportations, and also it's include the temporal detail here. Is identify the weekday and the or the weekend of this transportation. So basically, this one is the raw data that show the volume of this transportation through the train network, and it will also include the characteristic of the temperature and the climate of that day. So we can use this data set as the example, and we can explore the relationship inside this data. So we can use this library to create the to create the descriptive statistic table here, and yeah, you can just install this package in your R environment, and then call this package, and you just use this command to create these statistical summaries. So I think, yeah, it's very convenient to use just a few command lines to generate the descriptive statistics table. And similar to other statistical software packages that can generate this statistical summary quickly, like in Stata or in SPSS, that you can also do a few clicks and generate this table. And I think the next one, we can use some tool and some libraries to explore the data. Okay, before we run the regression, we need to understand the data and try to explore the relationship or the fundamental of the data. And this example showed that we can check the correlations among variables. So you can use this library, the correlation plot libraries, and you can use this code to test or to do the correlation matrix. So this one will use the variable, okay, inside this data set, and come up with this correlation matrix. And again, I think this one is similar to other statistical software packages like R or like Stata or SPSS, that they already provide this function as well. And you can also visualize this relationship. You can use this command to generate the plot or the variance, the correlation matrix here. is show the correlations table among variables. It's also use the bubble to represent the degrees and the directions of the correlations. And also we can use the histogram or the box plot commands here to generate this visualization, which is the statistical distributions of the volume, which is the main variable here, is the volume of the packages or the volume of the commodities that were transported through the train network in this data set. And then we can also generate the box plot here. And I think this is the main part of the simple regressions, that we can use these libraries to do these calculations. Yeah, so first thing first, we already installed this library. So now we just call or include this library into our code or into our process. And then we use this one line of the command to generate the regressions. Okay, so this is the R environment. I know that this might be inconvenience for some of you or some people. Even myself, I have some programming experience in like C++, Java, and other old languages like Fortran. But when I first use R, I very confused with the syntax, with the structure. So it takes time to get used to our environment. And I think the unique characteristic of our syntax is this one, is the arrow sign here. So it's the process here on the right-hand side of the arrow sign. So we call the linear regressions command here, LM. And we need to include these options to identify the dependent and independent variables. So the dependent variable is the volume of the transportations of the commodities by train, right, in this data set. And we want to understand how the high temperature affect the volume of the transportations. So we just do the bivariate analysis here. Okay. The dependent variable is the volume of the transportations, and the independent variable is the highest temperature or the maximum temperature on that day. And we have to use comma to separate the other argument. And the next one is the data set. So we already use the existing data set, which is the rail trail here. So this is a simple command without any additional options. Okay, so just a simple OLS regressions, just the name of the data set and the name of dependent variable and the name of the independent variable, and the output will be kept in this one. This is the variable, but it's the variable that based on the it's a object-oriented programming. So this one is like object. It's not just the variable. So this object, the simple model, will keep the result of these regressions, and you can explore the results here, or you can look into the structure of the object here, the object of the simple model, which is the output. So if you use this command print simple model, you will get this response. So it shows that we just did this regression, just two variables, and we use this data set, and the output is the coefficients of the linear regression. So this one is the intercept term, or the beta 0, and this one is the slope, or beta 1. So the response or the output just show very basic informations of this result, the slope and the intercept terms. And we can do the alternative commands that also show the results here. So we can use the command of coefficients, and we use the input as the simple model object, which is actually the output from our previous process. This allow me to erase this one. Okay, because this is the first process that we did earlier, we run the regressions and we keep the regression in this object. And then we can use this object as the input for this command coefficients. And the result of this command will be kept here. Okay, will be the result in coefficient objects. Okay, and if you call the coefficient object, it will show the detail inside this object, which is still the coefficients of this regression, the intercept term and the slope terms. And we can visualize the results, but we need another libraries. So we need this library to generate the graphs. Again, you need to first install this library and then use the install package, right? And then you can call or you can include this library here by using this command. And then we can plot the result from this regression. Again, the result of the regression is kept in this object, simple model. And we just use the system or the environment of the ggplot2, which is actually the package, the other package. But this simple command will generate this result, which is the line chart that represent the result of our calculation, which is the straight line or the linear model that represent the relationship between the high temperatures and the volume of the transportations. And I think let us switch to R, and then we can look at the first step of the calculations. So this is my screen. I just installed the latest version of R and RStudio, and this is the environment of RStudio. And I think it's very user friendly. You can import the data from this one, from the top right windows. The output mostly the graphical output will be generated here, and you can open the code here and also look at the response of the plum here. So first, I would like to open my file, which is the code that I share with you. The first one, code number 1 with OLS. Okay, this is my code. First, you have to install these packages. But as I mentioned earlier, if you use the latest version of RStudio, I think RStudio will detect this line of command and it will automatically recommend you to download and install these packages. So you may click on install to allow to download and install these packages. And I think I make a mistake earlier. I think I put the comma here. So you have to erase the comma in my previous versions that I distributed. And then you can run this code as well. You can highlight and click on run buttons to install these packages. Oh, yes. Okay, I got some messages in the text box. Okay, this is the code. I'm not sure that you already learned in the previous week about the options that you can modify uh, the color and the setup of the windows here. So you can go to Choose Terminals and select Terminal Options and select Appearance, because there are big collections of the appearance that you can switch or you can select, because some people prefer to use the black background. It's easier to navigate and to identify uh, the particular section of the code. So yeah, you can go to Tools and then Terminals and select Terminal Options, and then go to Appearance. And here you can adjust the size of the text and also the font of the text. And you can also change the backgrounds and the colors of the editors. Okay, let's do this one. I may increase the size. Was too big. Size of the text. So these are the code that I explained earlier, that uh, you first have to install packages, and um, you can do a step-by-step activations or step-by-step calculations. You just highlight the targeted area and then click on Run buttons. Then you will see the response here in these windows on the bottom left windows. Maybe I just use a simple color like this one. And again, I show in my lecture note earlier that first I use this command glimpse, which is the quick look, right? A quick look at the data set. And the data set is already embedded, so we don't need to include or import the data set. If you highlight just this section of the code and click on Run, then you get this response in the prompt windows, and it show the outlook of the data set. So you can do the step-by-step activations. Then you can highlight the next line of the code and click on run, and this will show the next results, which is the statistical summary of the data that we have. And again, we can do the adjustment. We can maybe enlarge the results here, and you can save the results. Because this one is the visualized results, you may export the result as the image. Okay, just go to the bottom right windows, and you can adjust the proportion of these windows, and you can also zoom or create the new windows here, and also you can save these results as the new file, as the graphical files. So let me share with you that, okay, first we install the libraries. I hope you already done with the library installations, but it depends on the internet connection. It depends on the speed of your computers. Maybe this set of the packages might take 5 minutes to do the complete installation. But if you already done with the installation, you may start with the step-by-step activation of the code. You may first try the first line of the code, which is the glimpse command, which is the quick look into the data set. And you can also activate ST, which is the descriptive summary of the data. And then this one do the adjustment is actually remove 2 columns from the data set, from the original data set. So it's remove column number 10 and 11 from the original data. And then we can compute the correlation matrix here. And the result is displayed here in this box, in this plum windows. But we can also visualize this result, but we need the libraries. We need the new library, which is the correlation plot libraries. So you have to call the correlation plot library first, and then activate the commands to display the correlations matrix here, the visualizations of the correlation matrix. And we can plot the histogram and the box plot. We can just highlight this line and activate this command. So you will get the result in this box, right, in the visualization box here. And again, you can save or you can activate this window and adjust the proportions of the chart. If you want to have more detail or you want to enlarge the chart here or the graph here, you can do so here. Or you can minimize the size of the chart. And after you do this adjustment, you just do the right-hand side click, and you can copy this image, or you can save the image as the new files. So this is very convenient for us when we activate the calculations and then we visualize the results. We can use this zoom button to adjust these pictures, and also we can save these pictures. So for all results, you can generate and also adjust these proportions. Yes, we can do the right-hand side click and copy the image, or we can save the image. Okay, so this is the first explorations of the data that we want to take a look inside the data set, and we want to explore some relationship of the data. But again, the main variable in the data set is the volume, which is the amount of the transportations. And then the next one, we will do the main part of this example, which is the regressions, the linear regression. So I mentioned earlier that for R is really simple. We need just one line of the code to activate the OS regressions. So we can first use the LM command, and then we have to identify the dependent variable, which is volumes. And we have just one independent variables, which is the high temperatures. And we need to connect them with this symbol to identify that the one on the right-hand side of the symbol will be the independent variable. And this is the data set that we use. And then we can print the results. So you can highlight just these portions and activate the calculations. Then we get this result, which is the coefficients of the model. We have the intercept term and the slope. And yet we can extract coefficients from the output, because the output is kept in here in the object of this one, of the simple model. So you can extract the value of the coefficients by using this command, and the output will be kept in the coefficients object here. Okay, then if you activate this one, you get uh, the same result, which is the coefficients, which are the slope and the intercept term. And then we can visualize the results. Again, we need another library to do these visualizations. We use Mosaic package, right? And we have to include this package in our code by using this line, the library commands, and then we can activate the plot here or the visualizations here. So the output is displayed in these windows and the bottom right windows. And again, you may click on zoom buttons and adjust the proportions of the pictures here. I know that we need to fit the picture in our presentations or in our report. So maybe we need to minimize or resize the pictures. Okay. After this modification, you may do the right-hand side click and you can copy the image, or you can save the image as the new picture files. I think this is very convenient for us to adjust these visualizations and also keep the result in the picture format, or you can directly copy this image and paste this one in the Microsoft Office, like presentations or in the report. And now we can do more calculation. We can explore the detail of the the good depth of fit of the model. So let's switch back to the let's go back to the PowerPoint. So earlier we just learned how to do a simple regression. We learned how to do simple statistical explorations like the correlation matrix and the box plot. And then finally, we can come up with the regression results. And we can explore more detail of the regression result here by using summaries, and you have to use the name of the result, the name of the object of the result here, simple model. And then it will show the distribution of the residual. But I think this one is very difficult to understand. I will show you later how to extend this part to understand how the residual is distributed. But I think the main part is here, that we have the value of the intercept term and the slope. And then we have standard errors. And with the standard error, we can do the t-tests, right? And then we can compute the p-values. So this result will show the statistical distribution of each coefficients. And basically, we prefer to have each coefficients that is very, very different from zero, because this one is the t-test. Here we're doing a t-test, and we want to make sure that the obtained value here is very far away from zero. Like in this first term, the intercept term, let's go back to simple statistical analysis here. We have the mean of the intercept, which is minus 17.079. And then the standard error is quite big. We have standard error of 59.395. So if we compute the t-stat value is very low. And if we compute the probabilities is 0.774. So actually what we are doing here is the test against zero. We can use the plain language to explain this test, that we want to make sure that the coefficient is different from zero, or the value of zero is not included in the two standard deviation range of these obtained results. But for the first term, or for the intercept coefficients, the final result show that I'm not, sorry, 77.4% sure that the distributions, or the statistical distribution of the intercept term includes zero. So it's very likely that the intercept term can be zero with this interval, or this confidential values is 77.4%. So we cannot say that the intercept term is very different from zero, or it has a very low chance to be zero. But the result for the high temperature variable, we have the value of 5.7, which is the slope term, and we have these standard errors. And when we do the t-test, we get the value of 6.7, and the p-value is extremely low. We can say that this is practically zero. So the results show that if we look at the distribution here, it's like we have the mean of the slope is 5.7, and the standard deviations standard error of the slope is only 0.848. So when we compute the t-test that we test against 0, we get around 6.7. So it means that the distance from the mean to 0 is around 6.7 times standard deviations. So when we plot the distribution, the chance or the opportunity that this obtained slope will be 0 is very small, or practically it's very, very unlikely that the slope will be 0. So we can confirm, or we can conclude that this regression has the significant value for the slope of the high temperatures. So the high temperature will induce more volume of the transportations. So I think this is the main part of the results. And I think the slope is very important, because if you come up with the slope that has more opportunity to be 0, it means that your x or your independent variable might not be the most influential one to induce the value of dependence one, or the y or the dependent variables. Okay, so basically we try to test each terms against zeros by using t-stat, and we want to make sure that it's different from 0, or each value is very, very unlikely to be 0, because if each term is more likely to be 0, it means that it's the value of x, or the value of independent variable, will not influence y, or influence independent ones. Oh, sorry, make a mistake. The value of independent variable will not induce the dependent one if we have a high p-values. And this one will show the R square and also the f-stat of the regression test. And also you can do the ANOVA analysis, which is the residual test, the analysis of the residuals. And actually the package already compute the value of R square, but you can do it manually. If you prefer to compute R square manually, you can follow the formula that compute the value of R square, and you have to first compute the SST, which is the total sum of square terms, and then you have to compute the value of SSE, which is the sum of square residuals. And also you have to compute the SSM, which is the sum of square that explained by the model. And this step will manually generate the value of the R square. Or you can use this command, the R square command, and use the input as the name of the model, and this will automatically generate the R square. Okay, so this is the I think I would like to switch back to R. That we already did the calculation earlier.
Professor Nat,
Yes.
sorry, before continue, I think we have a question regarding the data. Where is the data set is taken from? And how you set the seed can be another number? How we should set the number of seats?
Can I hold questions and I come back to answer later?
Okay, sir.
Okay, so this one will sorry, I will come back to answer after we finish this exercise. And so first we can compute the R square manually, like I shared with you earlier in the PowerPoint here. So if we highlight this portion of the code, then we can obtain the value of the sum of square error, sum of the square of total, and then we can compute the R square. Or you can quickly compute R square by using this one, the libraries, the matrix library, and you just use one line of this code to compute the R square. Show the test, which is the analysis of the residual. Because I introduced earlier that for the linear regressions, we prefer to have the residual that satisfy the conditions, which is the actually the variance covariance matrix of the residual that follow the theory and is follow the normal distributions. So the assumption of the simple linear regression assume that everything has the normal distributions. The value of output of y is the value that based on normal distribution. The value of the input, which is x, or the independent variable, also based on the normal distributions, and also the value of the residual is based on the normal distributions. So if you have the normal distribution of the residual and you compute the variance covariance matrix of the residual, then you get the matrix that has the variance in the diagonal terms and the covariance in the off-diagonal terms. So sorry to maybe go deeper into the matrix algebra, but this one will determine the quality of the regressions, because if you have the residual term that follow the normal distribution, you will get the high quality of your results, because everything follow the assumptions of the normal distributions. But for the result, even though we already computed the intercept term and the slopes, but we still need to check the properties of the residuals. So these are the lists of the property of the residual that we can use the command on R to check the distribution of the residual. First, we can use the residual plot to visualize the distribution of the residual or the error terms. So we want to obtain the residual that has the stable variations, because it ensure that we will get the normal distributions. But in this case, you will see the blue line here that show the the change of the variance of the residue that depends on the value of high temperature. So this one notify that we have the anomaly in our residue, because the property of our residue does not follow the theory. We prefer to have the basically the white noise or the randomly distributed residue. But now we can detect a pattern in the residue, and the value or the distribution of the residue depends on the value of the temperatures, which is our X or our independent variable. So we can conclude that our residue does not follow the normal distribution, and this is the first concern for the quality of our regressions. And this one is actually the test of the heteroscedasticity. It's the characteristic of the residue. We prefer to have the residue that is truly randomized. There is no pattern inside our residue. It's totally randomized. But in this case, we detect the patterns. The variance of the residue depends on the value of the temperatures. Okay, so we can visualize this relationship, and we can use the test. I think it's the Bush-Pagan test in the textbook. I think most textbook call this one as the Bush-Pagan test to verify the distribution of the residue. And in this case, we get this p-value that reject the null hypothesis. Okay, and the null hypothesis say that we have the normal distribution, but in this case, we reject the null hypothesis. So we have the pattern in our residuals. And the second test is the outliers. We can perform the outlier test and identify the serious outlier in our data. But in this case, we get these p-values, and it does not reject the null hypothesis. So this result say that it's okay for our calculations. We don't have the serious outlier in our data. And the next test is the Durbin-Watson's. It tests the autocorrelation among residuals. And in this case, we have the value that close to 2. Our preferred value is the Durbin-Watson statistic that is close to 2. And the p-value is not significant. So I think in this case, we don't have the problem in these values in this residue. And the last one is the Shapiro-Wilk test that try to verify the normal distribution of the residue. And then we get this statistical results, the p-values. So I think this is the set of the tests that we can do after we run the regressions. We can use this set of command to verify the characteristic of the residue, because basically we want to obtain the normal distributions for the residue, and that will give us the ideal variance covariance matrix. And the last one is the plot that allow us to plot the band. It's actually the band of that show the heteroscedasticity of the results. So the band is volatile in some area, in some value of the volumes. And we can extend our regressions. Earlier is just the case of just one independent variable, but you can keep the same command and extend just this one. So the list of independent variable, and then you will get the results of the multiple regressions. So the output will show the table, which is the list of the variables here. And then we get the value of the R squared here. And also the value of the F test, the F statistic. So the F test here, in this case, it's very important because it's ensure that all of the independent variable are jointly explaining the results or explaining the variations of the y or the dependent ones, the dependent variables. But this one also identify the significant level of each variables. So if you have 3 star is really close to 0, so it means that that particular variable is very important. And if you have just 1 star, it's just 5% level. And if you have a dot, it's just 10% level. Okay, let's switch to the R. Okay, we can use these two libraries to do this test. The first we can activate the residual plot, which show the relationship between the value of the residual and the temperatures. So we come up with this blue line. It shows that actually the residual, the size or the variance of the residual depends on the temperatures. And then the second one is the test for the heteroscedasticity. Okay, so in this case, we have the significant levels. So it shows that actually we experience the problem of the heteroscedasticity. And then we can do the outlier test. But in this case, we can reject the null hypothesis because p-value is not significant. And then we can do the Durbin-Watson test for the autocorrelations. In this case, in this case, we have the value that's, I think it's okay. We don't have the autocorrelation problems because p-value is not significant. And the last one is the test for the normality of the model, sorry, of the residual. But in this case, they say that we cannot reject the null hypothesis. So I say that mostly the residual are normally distributed. And the last part of the code will generate the graphical plots or the graphical representation of these regressions. So I think it's very nice to have these results, right? That you can also adjust the proportion of the size of this plot, and you can save or copy this result and use in your report or in your calculations. Okay, I think let's have a break and we come back. Okay.
Yeah. Okay, sir. Now we will have a short break for 5 minutes, so we can go back and start the session again at 10:27. Thank you. Udah. All right. May I check if everyone's back to the floor already, or still need some time to grab a coffee or food? Please, uh, show your response. Is everyone here? Oh, before we continue the session, Professor Nat, may I check if our participant can follow your explanation so far? So, anyone facing difficulties in following Professor Nat explanations? Anyone? Anyone wants to respond? Or as usual practice, if you have question, you can write it to the chat box. Professor Nat will respond later. So silence means everyone's can follow. Yes, thank you, Miss Young Tai. All right, so I will pass the floor to Professor Nat. Please, Professor
Okay,
Nat, continue.
thank you very much. And I would like to go back to answer two questions. The first one, the real data is actually included in mass package, this one, the mass package. So it's already embedded in the package. And so that's why we don't need to import the data, because it's like the popular data set for the demonstration or to the tutorial sessions. Second one is the seed. It's about the seed. I think for most of the R user is the endless discussion among us. You may Google the question like the most appropriate value of the seed in R, and you will see a lot of people are trying to argue or try to propose the appropriate value. But my own conclusion is that there is no appropriate value for the seed. But first, the seed is just the maximum like the maximum memory or the maximum uh, empty box to keep uh, the uh, sorry, it's called the randomized values, or the randomized uh, like the something that was randomized in your calculation, like when you do some bootstrapping or some Monte Carlo calculations that require the randomization in the process of the calculations. And the seed will allocate the memory for computers to keep those randomized value. I think the most important one is uh, the same seed value to ensure that you get the same result of the calculations every time that you run the code. If you use the same seed numbers, you will get the same results, exactly the same result. Yeah, particularly when we apply uh, the process that need to do the like the randomization to extrapolate the sample, or to do like the enlargement of the calculations, like trial process in the calculations. Okay, I think we may move to the next example. And the next one is the case of Thailand. So first thing first, I would like to delete uh, the um, the existing data. So I just click on uh, this one. I clear the memories. I delete all variables and delete all visualizations. Okay. Or you can use my code that I shared with you earlier, so that we can uh, clear everything by using this command line. The RM list here. Okay, so let's take a look at the case of Thailand. I share with you the data and the code. So this is the code. Let me erase. Okay, so this is the code for the case of Thailand. So actually it's the modifications of the previous one that we use in the previous example. And I already distributed the data set. Is the spreadsheet. And if you open this one, it's the Excel file. It's extracted from the socioeconomics and industrial census in 2010. The first three columns is the proportions of the labor in that province. So this is the provincial levels. So we have 76 provinces in Thailand in 2010. So the first three columns show the proportions of the labor in each activity: agriculture, manufacturing, and service. And then the next three columns are the logarithm of the corresponding one. And then the next column, this one is the industrial density. So I already computed the logarithm one. So it's the ratio of the industrial output in currency unit, which is baht in Thailand, and it's divided by the industrial area in that province. So this one will measure the intensity of the industrial production in each province. And I obtained this value from the industrial census. And the next one is the nighttime light. So this is the satellite data. I use this satellite image to extract the density of illumination at night in that province. So this one is the average density of the nighttime light in each province. And then the last one, the last column is just the logarithm of the nighttime light. So this is the data set that I would like to use in this example. I think this is related to the actual practice that usually we have the data like this is kept in the spreadsheet formats, and then we have to import the data. So we can select here, import dataset, and select from Excel, and then click on Browse, and I select this one, my Thai dataset in 2010. Click on Import. Then we have this dataset for 76 provinces, and we have 9 variables. So I just modified the code that we did earlier, or we used earlier. But because this one is the manual process to include the data, so you have to be careful, because actually this line should be disabled in your code, because this is the location of the code on my computers. But now we already import the data here, and the data is already kept, or the computer already notified the data as the object here, this name, and it's shown in the data set here. So when you do the manual data imports, you have to disable this line, and you have to make sure that computers are already recognized or already imported this data set. So in this case, it's already know this data set. And then we can repeat the same process. We can run the first line, which is the glimpse, which is the first look of the data structure. So it will show the basic format of the data. Or we can compute the statistical summary of the data. I can activate this line, and this will automatically generate the statistical summary of my data. Or we can do the correlation matrix here. Or we can plot the correlations matrix here. And yes, you can adjust the size or the proportions of this matrix. You can test the historical, sorry, the histogram of the industrial density, and also the box plot of the industrial density. So in this example, I would like to do simple regression. I would like to explore the relationship between the nighttime light, which is the density of the light at night, and the density of the industrial production. So my command is here. It's just this minor modifications of the previous code. My dependent variable is the logarithm of the nighttime light in that province, and my independent variable is the logarithm of the industrial density. And I have to identify the data set that we will use, which is this Excel table. And then we can run this code, and it's come up with these results. So this is the quick result here. And the intercept term is negative, but we get the positive slope, which is expected, because if we have more industrialization, we should observe a higher density of the illumination at night. And again, we can use the same code that we did earlier and extract the intercept term for both the for both the intercept term and slopes. And then we can plot this relationship. Okay. And then we can zoom, or we can adjust these windows. Yeah, this is the results. So it's I think it's very nice, right? Highly correlated one. We have a nice relationship between the industrial density and the illumination or the nighttime light from the satellite. It's highly correlated. And we can do the table of the statistical results here. In this case, you get the statistically significant for both for the intercept term and the slope term. If you look at the p-value for both, you get a p-value that is very, very small. So both are practically zeros, right? So both are significant. And the R square is, I think it's quite high. The R square is around 73%. Okay, 0.3, so 0.7357. So we can explain the density of the light by using the density of industrial productions. Industrial production can explain around 73% of the variation of the nighttime light. And then we can again do the analysis of the residual. We can do the residual plot and test the heteroscedasticity. The first test is the Buch-Pagan test. And then we can test the outlier, and we can do the Durbin-Watson test for the autocorrelations. And the last one will be the test for the normal distributions. Okay, so I think this is the example that we can use the code, the original code, and do some modification with our data. So in this case, I prepare the data from the actual surveys, from the actual census that originally produced by Thailand NSO. And I integrated the data with the nighttime light index that I obtained from the satellite. Yes. And I think we have very limited time, so may I move to the next issue? Oh, I'm very sorry that I got the message and some of the attendants have not received the data set. Oh, I already shared the data set in the chat box. Okay, so let's move to the next one, which is the next modifications. So basically, GLM is like the extension of the conventional linear regressions. And I can quickly share with you that the modification is based on the distributions of the data. Because we need to consider the statistical distribution of each variables. And if the variable cannot satisfy or they don't have the normal distribution properties, then we have the problem with our conventional linear regression, and we need GLM to allow us to still perform or to do the linear regression with those data. Okay, so this one I use the data from this source is the Quebec Center for Biodiversity Science. It's the Canadian Research Centers. And from my own survey, I found that this is the best resource, the best materials for studying and practicing the family of GLM, LMM, and GRMM. So the rest of the topics that we will learn will follow or will use these original materials, but I include some modifications. And again, I have to acknowledge the contributions of the expert who produced these original materials. Okay, so this is the original materials, and I already included the link. You can click on the link to download the booklet to download the original PowerPoint and original code and also original data. And if you have the experience of using GitHub, you can go to this link, which is the alternative source of the data. All of them are available on GitHub, and you can activate the calculations on GitHub. Okay, this is the list of the expert who produced the original materials. Okay, so first thing first, we have to go back to the main issue here, why we need GLM, why we cannot apply conventional or the basic linear regression to our analysis. This is the main problems because for the simple linear regressions, we assume that everything has the normal distributions. Everything is normally distributed, and in practice, we cannot come up with the data set that satisfy that conditions. That is the main reason to use GLM instead of the conventional basic regressions. And again, we need I think three main elements of the regression to follow the normal distribution assumption. First, the dependent variables or the response variable has to be normally distributed. The predictor or the independent variable have to be the normal variable or the normally distributed. And also the error term or the residual that we obtain from regression also has to be normally distributed. And these are the main assumption for the basic linear regressions. And yeah, in practice, it's very difficult to obtain or to satisfy all of these conditions. And again, let's take a look at the basic regressions. Y is the output or the response variables. X is the input or the predictive variable or the explanatory variable. And we need only X and Y in our calculations. And then we can come up with the slope, the intercept term, and the error terms. And in the conventional simple OS regression or the simple linear regression, all of these terms, all of this value have to be the normal distribution. It has to be normally distributed. And again, it's very difficult to satisfy these conditions. And again, I would like to share with you that this is the basic assumption of the simple linear regressions that we try to explain the relationship in the linear form in the straight line equations. And we assume that the variance of the error term is constant. And the variance the variance is constant, and we assume that the covariance has to be 0 or there is no autocorrelations among the residuals, and the residual has to follow the normal distributions. So these are the main assumptions. And if you can come up with a good data set and all of the data are based on the normal distribution, then you get a nice result and the nice property like this one. Okay. And to understand or to do this the simulation, you can simulate the results that we can generate the independent variable, and we can use this generated independent variable to run regression, and you get a very nice results. Because okay, sorry for skipping this. So this one is the code that try to replicate the ideal regressions, the ideal case of the simple linear regression. We have the independent variable that has the properties that follow the theory. And then if you run the regressions and analyze the residual, you get the very nice results like this one, that the residual is purely randomized. Okay, there is no pattern in the residual. Either it's just the very simple plot between the y values, the output, and the residual, or you try to standardize the residual and plot this chart again. So this one is like the modification of the first one, that you standardize the value of residual and plot this value against the output, the dependent variable. Then we have the random pattern here. Or if you use the QQ plot, which is the test of the normal distribution of the residual, and is try to order the value of the residual based on I think it's quantile, and it's show that if you have the residual that follow the theory, is to have the residual that is normally distributed, the result will be scattering around this 45-degree line, which is the ideal case. Or you can do the it's called the Cook distance. This one will explore the outliers, or is try to identify the outlier in your data set. And if there exists the outlier, you will see some points that are located very far away from the mean or from the middle line. Okay. So the Cook distance is the techniques to identify outlier in your data set or in your regression results, and it's try to remove one sample from the total observation that you have and run regressions, and it's keep doing this again and again until the last observation is performed or is removed. It will check the results from removing one sample, and if the result is much different from the normal or the mean, it can identify that that one could be the outliers. So again, I think this page show that if we have a very nice data set that follow the theory, everything follow the normal distribution, you should come up with the residual like this one. The residual of your regression will be very nice like this one. It's satisfy all conditions for all tests that you apply to the residual. Okay. If you test the normal distribution by using QQ chart, it will be scattering around 45-degree line. If you use the scale location plot here, you have no patterns in this result. It's totally scattering or it's totally randomized. So there is no heteroscedasticity problems. Or if you use the Cook distance techniques to remove each individual observation from the regressions and observe the obtained residual, then again, there's no obvious outlier in this result. Everything is just scattering around the mean value, or it's just randomized. But in practice, you might experience the totally different distribution. I think all of you are statisticians, you know that actually when we do the survey and when we collect the data, we might come up with a different statistical distribution for each variables. And again, this example use the data set that is the actual one, the actual survey in Canada, and they try to collect the data of the biological, the samples is the mite, is the small insects, and it's try to also study the environmental factor that is related to the mites in that locations. So there are 70 observations in this data set, and it's come from the research unit in Quebec in Canada. Wait, this is the outline or the quick look of the structure of the data. So there are 9 variables in this data set, and there are 70 observations. Okay, so I think first we can separate 8 variables into 2 sets. The first one can be the response variable, or it can be dependent variable. And the rest of the data are the independent variable or the predictive variable. So first we have the occurrence. So PA is actually stand for present or not present or not available or in that area. So it's actually binary data, either 0 or 1, that we can find specific species in that area or not. And the second one is the abundant data. So this one is like the count or the integer numbers. And the last one is the proportion or the relative frequency of that particular species in that area. So basically we have 3 different statistical distribution of the variable. The first one is the binary data. The second one is more like Poisson distribution, that you have discrete number. And the last one will be like the frequency data. Okay, so we have totally different statistical distribution for each one, for each responsive data, so responsive variable. And then we have the predictive variable as well, that also have different statistical characteristic as well. So I think this is very challenging because we try to relate the relationship, and yeah, you can map or you can connect the pairwise relationship. Like the first one, you can you can predict the abundance of that species with the water content in that area. Second, you can compute the proportions of that species with the water content data. Or alternatively, you can compute the occurrence of that species with the number of the vegetation or the shrubs nearby. But I think in this example, they try to show 3 pairwise relationship Okay, the first one is the second dependent the second dependent variable, which is the abundance of that species with the water content in that area. And the second one is the relationship between the water content in that area and the binary data, which is the occurrence of that species in that area. And the third one is the proportion of that species in that area and the water contents. Okay, so we have three different relationship. So the first one is the relationship between the water content and the abundance. So if you plot this relationship, it will be like this one. So abundant is the count, or the discrete number is the number of the mite that can be found in that area. So the second one is the relationship between the continuous value, which is the water contents, and the binary value, which is the of the present or the absence of the species in that area. So you get binary variable here. And the last one is the case that you have the frequency data, the relative frequency data, and the continuous variable, which is the water content in that area. So this is really challenging because if you just apply simple linear regression like the previous example, so this is the command line, the command on R to run the linear regression between the first pairwise relationship. It's a simple code here. And also, again, you can run the simple regression with the second pairwise relationship between the binary variable, the present and absence of the species and the water content in that area. And the third one is the relationship between the probability or the frequencies to find that species and the water content in that area. And when you run this simple linear regression for the first case, the first pairwise relationship, you get a nice result here. You get statistically significant results for the slope, right, for the water count. And again, if you look at the result that you obtain from the second one, you get this regression results, and the last one here. So you get the slope for each one, for each case. And all three models are statistically significant. But the serious concern is the quality of the results or the quality of the regressions, even though you get the statistically significant slope coefficient for all regressions. Right. We have three regressions here. And this is the serious issue. This is the analysis of the residual for the first regression. You will see that you have the result like this one. You have two variables, and you try to approximate the straight line that represent the relationship between these two variables. Right? But the error term will be like this one. So we can do 4 tests for the residual, and you will see that the residual is not randomly distributed. You see the clear pattern of the residual for the first one, for the plot between residual and the projected values. And the second one for the QQ plot now is not the nice distribution like we we got in the trial, because we prefer to have the result that's scattering around the 45-degree line, but now it's not the case. It has the different distributions. And then if you do also the plot that show the distributions between the predicted results and the standardized residual, you will see the clear patterns of the residual here. And also for the last one, you will see the clear pattern here. So we first run a simple regression between two variables, the water content and the number of that species. And then with the statistical distribution that is different from normal, you get the residual term that are much different from the theory or much different from the normal distribution assumptions in the theory. Now we have some pattern that does clearly show that the residual is not the white noise. The residual is not randomly distributed. There are clear patterns inside the residual. Okay, and this will follow the theory, is show that the coefficient that we obtain from the simple regression is not appropriate. It cannot be the blue or the base linear unbiased estimators. And this is the second case that we try to use the simple regression to approximate the straight line that explain the relationship between the probability to find that species and the water content in that area. And again, if you do the full residual analysis or full tests on the residual, there exists the clear patterns in the residual. So the residual is not randomly distributed. So this one show that we need to correct or to modify this regression. We cannot use simple regression to analyze this pairwise analysis. And again, for the QQ plot, it's not located on the 45-degree line. And this one is the last pairwise example. Is the relationship between water contents and the binary variable. I think you can guess the result if you have the binary variable. If you try to run the binary variable against the continuous variable, you will come up with the result like this. And then your residual will be the binary one like this one. But the distribution of the residual show the clear patterns of the relationship. Okay, so in this case, we have to go back and again understand the assumption of the conventional linear regression, that we assume normal distributions, and we assume that the variance of the slope or the variance of the estimator will be constant. Okay. But in this example, the variance of if we assume the variance that is constant, we will come up with this result. That is the mistake here in this area. So basically, we can conclude that if we have the combination of the variable that do not follow the normal distribution, we need to modify our regressions. First thing first, you may modify your data. You may take or use the logarithm to transform the data. It's like I did in my previous exercise in the case of the nighttime light in Thailand and the industrial density in Thailand, that I apply the logarithm scale to both data to make it fit to the linear regressions. And again, you can use the logarithm scale or apply the logarithm to modify the raw data. But this is not the complete solutions, or you cannot apply this technique to all cases because you may deal with the discrete values like the integer or the count values. You may deal with the continuous values, and you may also have the binary variable in the data set. So this will cause a big problem to our simple regressions. And that's why we need to do GLM. We need to use the generalized linear regressions to modify the data and modify the form of regressions to fit the data, or to finally use the conventional linear regression to fit the data. And I think let me skip to this one first. So the main idea of the GLM, or the generalized linear model, is to transform the data, and then after the transformation, the data can fit the conventional linear regressions. And to do this, we need to first transform the means, and also we have to transform the variance. So we need to do both the transformations of the output or the expected value, and the transformation of the variance of the residual. And in R, you can activate this calculation by using GLM, the generalized linear model. And there are the collections of these options to identify these modifications. So I think the most important part to do GLM on R is to select the appropriate modification or appropriate link functions, or the appropriate modifications to the original data. So this selection based on the distribution of the raw data. If you have the raw data that are normally distributed, it's easy. You can just use these identity options. But if you have the binary data, or your prediction is binomials, then you have to use the logit options. So this regression become logit. Okay, or it's become the logistic regressions. Or if you have the data that follow the Poisson distribution, you have to do the logarithm transformation first. Or if you have the data that follow the gamma distribution, you have to identify that you need these options. You need the inverse option here, and this will transform the gamma distribution into the format that allow us to do the simple linear regression. So for each option, it will transform the data, and it will allow the model to finally apply the conventional linear regressions to estimate beta, or to estimate the slope. Okay. So I think I can quickly summarize that. Okay, if you have the data that are not normally distributed, you need GLM. But when you do GLM, you have to make sure that the selection of the options match to the distribution of your data. Okay. So you have to examine your data before you select these options. Okay, so I think uh, the example in this case will show that uh, the original pairwise regression that we did earlier has to be modified. Like the first regression here has to be modified. The second, I think the second regression here has to be also modified with the GLM. And also the last one has to be corrected because this is basically the logistic regression or the logic regression. So you cannot just apply simple linear regression to do this one. Okay. So you have to transform this one into logic. Okay, so I think the material here try to show that for each pairwise example, you have to follow these modifications. Okay. And sorry. Okay, I think for the first one that they try to come up with the regression that predict the relationship between water contents and the number of that species. And actually, if you run the histogram visualizations, you will get these distributions. And it's actually the Poisson distributions. So you need to modify the data or you have to impose the option on the regressions. Okay, so we have to modify the code. And also for the next one, which is actually the logit regressions, you have binomial data, so you have to select the option of logit. Okay, so this is uh, the example of the code. So let's go to the code. I have some technical problem. May I excuse for 2 minutes and I will come back? Okay, sorry, just 2 minutes.
Sure, sure. Okay, well, waiting for Professor Nat to come back. As usual, if you have a question, you can write it through chat box or you can ask directly. And for your information, all the material that presented by Professor Natapong today and will be presented tomorrow is already on the share folder that I shared to you yesterday by email. So please go check there and download all the materials. Thank you.
Okay, so sorry for the interruptions, and let's resume our contents that I would like to share with you. First, the code, right? Code number 2, which is the GRM example. And again, you need to install these packages. It might take time, so maybe um, we have to wait until you already install all of these packages. Okay, so, if you already finished these installations, then you can highlight this part and activate. This portion will include these packages into our calculations. And the first part of uh, the code is just the simulations that we try to create artificial data. And this artificial data follow the conventional assumption of the linear regressions. We create this artificial data, which has the normal distribution properties for X and Y. And then we do the regressions, right? So this is the regression, this line, simple regression between X and Y. And X and Y are generated by this line. And the generation of X and Y based on normal distributions. So everything is ideal, is based on the normal distribution. If you run the code, then you get the result of these regressions. And if you, let's go to, okay, I think go to this one. Go to this line. Go to like 117. Or you may highlight this block from line 58 to 117 will replicate the result that I discussed earlier in the PowerPoint. So these are the result of 4 tests in the visualizations. Is the residual analysis that show the distribution of the residual based on the theory. So we have a very nice property here that the residual are normally distributed is the normal distribution. So we don't see any clear patterns of the distributions of residual in each test. It's totally randomized. But for the next part of the code, is we'll first import the data. So we have to do this one manually. And I already share this data set, mites.csv, which is the spreadsheet that include the data set that we will do the analysis here. So we will include this data manually. So we will go to this one. select on import dataset and select from Excel. And I will go to my dataset here. Oops. Oh, I see. It's not the Excel, it's the CSV. So we should use the first option. Select from text. And again, we have to go to my folders and import this one, nights.csv. Okay, so we have the data set here, which is the biological data set. So we included the data manually, and the data is already recognized here. It's already included. Now we can do the calculations. Okay. This will explore the basic structure of the data. If you activate head and the structure of the data, it will show the basic foundation of the data. And then we can plot the distribution of three variables. Actually, it's the three pairwise relationship that we would like to explore. The first one is the relationship between the number of the species and the water content in that area. The second one is the relationship between the water contents and the binary or the presence and absence of the species in that area. And the last one is the probability to find that species in that area and the water contents. So if we highlight this three blocks of the code and run, then we get these results. So each one show the pairwise relationship between water contents and the dependent variable. Water content is the continuous variable, but the dependent variable of these three pairwise analysis are not there. They have their own specific characteristics, and all of them are not normal distributions. And then this code will show how the results look like if we apply simple linear regression to each pairwise relationship. This will show the results here. Yeah. So this is the result for each one. For the first regressions, we get statistically significant results. For the second regression, again, we get the statistically significant result for both the slope and the intercept terms. And again, for the last one, we get the statistically significant values for both the intercept term and the slope. If we apply this code, it will extract just only the coefficients. It will extract only the coefficient of each regressions. And then it will show the residual analysis. I think I would like to do this one first, this block first. So it's the results that we saw in the presentations. So it's the residual analysis for each pairwise regressions. So you will see the obvious pattern in each one, in each residual analysis. And I think the interesting property of the result analysis is this one. It's already identified the number of the observations. You will see the small number for each dot here. And it's only identified the one that are likely to be the outlier. So like this one for this result, you will see number 1 here, number 14 here, and number 34 here. So these three number identify 3 observations in our data that are likely to be the outlier for the first test for the first plot here, residual and the predicted value. And for the scale one, again, we get this 3 value again. So it's confirmed that these 3 observations are likely to be the outliers. And also for the QQ residual test, you will see that these 3 observations are far away from the conventional line or the 45-degree line. So I think this is the benefit of using this command, because it will visualize the result of the residual analysis, and it's also automatically identify the particular observation in our dataset that could be the outlier. Okay, for this case, you get the number on the dots, and that are the suspects to be the outlier. Okay, so this show that even though we have a nice result, if you look at the slope and the intercept term from our simple regressions, you get statistically significant result for all 3 pairwise regressions. But the residual analysis show that we have anomalies, we have heteroscedasticity, and we have the anomaly of the distribution patterns of the residual. Okay, this one will show the results of the distributions. I think the most important part for this example is this part, this code that show the corrections of the problems. Because for the first pairwise relationship, the first pairwise regressions, we learned that the distribution of the columnar or the species is Poisson's. Okay, it's not normal distribution. So we have to specify here that we will use the GLM regressions, and still we use the same syntax here. We will do the regression for these two variables, and the data set is here. And we will use this modification. We specifically identify that we will treat these regressions by using the Poisson distribution transformations. So it will transform the data from Poisson distribution into the setting of the linear regressions. And I think again, if we look at the next part, I think the most important session is here, that in the second case, we try to do the regressions, okay, between the binary variable and the water contents here. And we need to modify our code so we have the GLM regressions, but now we have to specify that this is a logic regression, this is logistic regressions. So we want to transform the binary variable with the logistic equations, and then we can obtain the result that is actually the logic regressions. Okay, so I think this is the main part of the analysis that we need to correct our regression, and we have to identify the appropriate transformations. So and it totally depends on the distribution of the variable that we use. I think I would like to finalize my today's presentation here, that GLM is the extension of the conventional linear regressions, and are already provide a simple modification for your analysis, that you can just include the selections of the option here, the modifications, and that will allow you to do the regressions that is matched to the statistical property of your data. Any questions? I think tomorrow I will continue the contents with the next modification or the next extension. And but for today, I just would like to end the main context here, that before we run the linear regressions, we have to check the distribution property of the variable. And if we come up with the results that identify the specific statistical distribution for each variable, then we can select this option to match or to improve our regression results. So first thing first, before you run the regression, you have to check the statistical distribution of your data. Okay, thank you very much. And for tomorrow, I will upload the code and the PowerPoint again, and also the example.
Yeah, all right. Maybe before we end this session, I would like to check the participant first if they have questions. So, anyone have a question for Professor Nat? Or do you want to save it for tomorrow? Maybe some of us still need time to digest all the lecture today. Yeah, we have a lot to learn today. Even personally for me that have learned statistics, but it many years ago. So it's kind of a refreshment for me. And for your kind information, if you want to uh, learn and watch again this session, it is available on ASEAN Stat YouTube channel. So please go check there. So you can rewatch these sessions and you can learn again. You can uh, hear again the explanation from Professor Nat. To Professor Nat, thank you so much for today's sessions. And we expect more for tomorrow to dive more about regression model with your guidance, of course. And again, thank you so much, and see you tomorrow.
Okay, thank you, everyone. See you tomorrow. Yeah, take care. See you tomorrow.
See you tomorrow.